So in this problem, we have three forces acting on a body that moves with unchanged velocity, v equals 2I minus 7j. So we're given the velocity of the object, and we are told this is unchanged. We can actually see that from the formula, right? It doesn't depend on time, so yeah, it is constant. By F1 equals 2I plus 3j minus 2k, and F2 is minus 5I plus 8j minus 2k. The question is, what is the third force? So we're looking for the third force, and one thing I know is the velocity is constant. Once you see that the velocity is constant, one thing you can deduce is that the acceleration must be 0 for the velocity to be a constant. And then this means that F equals ma equals 0. This is F net. It means that F1 plus F2 plus F3 should add up to 0. Now, to get rid of the vector notation, I will split this equation along x, y, and z in this case because my forces have all three components. Namely, this is F1x, this is F2, this is F1y, and this is F1z. Similarly, this is F2x, F2y, and F2z. So I can use this and equation along x, I will get that f1x plus f2x plus f3x should add up to 0. Similarly, along y, is just, remember, what we want to find is f3. So I'll just substitute f1x and f2x, and I'll try to find f3x. So f1x is 2, f2x is minus 5, and f3x is what I want to find. As you can see, I can rearrange for f3x. I got 3 newtons. Similarly, along the y direction, you can see this is f1y, this is f2y. I'll just substitute these. So I have 3 plus 8 plus f3y, which is what we want. These should add up to 0, so f3y should be minus 11 newtons. And along the z direction, I have minus 2 for f1 and minus 2 for f2. Here they are. Equals 0, so f3z should be equal to 4 newtons. You can see how I found the components of the third force. I can now write the third force in unit vector notation, similar to F1 and F2. I found the third force in its unit vector notation. So what we're working on today is just defining some particular or common everyday forces. So far, we were talking about forces in general, and that an object can have multiple forces acting on it, and we could find F net, and from F net we can deduce what will happen to the motion of an object. But today we're focusing more on some everyday forces. We discussed some forces previously in general. I'm just gonna highlight more details on these. Namely, we talked about the weight force, the normal force, the tension force, and the friction force. And that's basically what we're focusing on. I'm just making one slide on each of these to highlight their characteristics so that we can work through more sophisticated problem solving. So I'm starting with our most basic force, which is the gravity of Earth. This is a force that exists on any object, any massive object on Earth. So in fact, any problem you see, whatever the situation is, so whether it's a book on a table, a book in air, a book in a basement, I don't care. It will always have a weight force acting on it as long as it is on or near the surface of Earth. So let me fix our statement. So I'll say on and near as well, because any object released from a non-zero height will also feel the gravity of Earth, right? And will go in a free fall, actually. So any object with a mass m, I'm gonna say one of the forces acting on it will be the weight force. Now let's look at some properties of the weight force. A weight force is a pull that acts on a body from Earth. So it's like the gravitational force that a body like Earth exerts on an object. I want you to notice that if the object was on the moon, it will feel gravity as well, but it will just have a different equation. Namely, the weight of a body exerted by Earth is equal to m times g, where g is the gravity of Earth. If we are on a different planet, g is the gravity of this planet. In particular, if an object is on the moon, it feels a gravitational force, but this gravity is less than that of Earth. Namely, g of the moon is around 6 newtons per kilogram or meters per second squared, whereas g of Earth is 9.8. We talked about it before. But for both, the exerted force is going to be, let's say I'm releasing a ball. The exerted force is going to be m times g. The difference is just that the value of g is not the same in each case. So this is our formula. M is the mass of the object in kilograms. G is the gravity of Earth or the planet we're interested in. One thing I should also add to you is weight is always exerted vertically. Or we can say it's towards the center of Earth or the planet. So if I'm studying a book on a table, I'll always draw the weight to be downwards. If I put the book, like I zoom out and I show planet Earth as a round object, as I did in this figure, the weight to be pointing towards the center of the moon or the Earth. Makes sense? Now, I wrote another remark for you. We can measure the weight using a balance, and that's something very common that we usually do to check the masses of the object. It's one way to measure the mass by finding the weight of the object, and we can measure the weight by using a scale. This is a scale, and this is also a scale, by the way. The difference between them is this is a spring scale. The spring scale contains a spring which gets elongated here, and it's well calibrated to show us the values of the force. Whereas this scale works by balancing the object with some known masses. So if I have the object here, I'll put, let's say, a 1 kilogram weight here, and then I can check the mass. Let's check this conceptual question. Compare Natalia's mass on Earth to that on the moon. So here, I want you to be careful about something. One thing I know is the gravity here is given, the gravity here is given, so we can compare the weights easily. So if I want to compare the weights, W is M times G. Oh, so it seems my value of the gravity of the moon previously was not very correct. This should be 1.6, not 6. Sorry about that. So I can compare the weight, Natalia's weight, basically. On Earth, Natalia will feel a pull from Earth equal to her mass times 9.8, whereas on the moon, weight will look like her mass times 1.6. She will feel lighter. She will move more easily. But be careful about the question. It has a small trick. We're comparing her mass. And remember, the mass was defined as the quantity of matter in an object. So if this is the same Natalia, it's going to be the same mass because we have the same quantity of matter, unless Natalia went on a strict diet during her trip from Earth to the moon, and then her mass does change. Otherwise, the mass is the same. So if I want to compare the mass on Earth, Natalia's mass on the Earth is the same as Natalia's mass on the moon. This is a small trick which you should be a bit aware of. If I'm comparing the weights, these are forces, but if I'm comparing the mass, these are not the forces that are going to be changing across different planets. So our second force is the normal force, which is the force exerted by surfaces to support objects that are in contact with this surface, essentially. It is always normal to the surface, whether the surface is horizontal or inclined. It's not necessarily vertical. Namely, I want you to see our three figures here. In figure 1, there is no normal force because there's no surface supporting the object. Whereas in figure, I'll just draw the weight force. In figure 2, I'll have both weight and normal force. So there is a normal force, and this force is perpendicular to the surface. So I have drawn it like this. It is vertically upwards. But look at figure 3. In figure 3, I have a normal force, but I'll draw this normal force to be oblique as such because the normal should be perpendicular to the surface. Surfaces support objects by exerting a perpendicular force on them. So make sure you draw the normal perpendicular to the surface. If the surface is oblique or inclined, I'll have to draw the normal force to be inclined such that it's perpendicular to the surface, all right? So I also have one more situation, which is the book on the table given here. This book is going to be feeling both a weight and a normal force, pretty easy. I can work on Fnet after that. I'll set, if the book is at rest, then Fnet, which is W plus N, is equal to 0. I can then project along X and Y. Along the X-axis, Nx is 0, Wx is 0. So this gives me 0 plus 0 equals 0. Along the Y direction, Ny is N itself, Wy is minus W, because this one is upwards, a vector which is pointing up. if you just draw a little x and y axes, you can see how the normal is in the positive part of the y-axis. So its y component, I'll write it to be plus n, whereas the weight is in the negative part of the y-axis. So I'll draw it to be negative w. Its y component is negative w. So this gives me that n minus w equals 0. Again, these are adding up to 0 because f net is 0. So projecting on the y-axis, you'll have f net y is 0, so minus w plus n is 0. What did I deduce here? I deduced that the normal equals the weight in this particular case only. One thing I want you to see, unlike the weight force, the normal does not have a formula. We find it by studying equilibrium. So I'll look at the scenario, I'll use Newton's law and find the normal force. So I'll write this as a remark here. The normal force doesn't have a formula. Namely, it is a reactive force. And it varies according to the equilibrium. And not according to a certain formula that is given to you. So we find it using Newton's laws, whether it's the first or the second. In this particular case, I used Newton's first law and I got this equation and I deduced that n equals w. So if you find the magnitude of the weight, you'll just deduce that this is the magnitude of the normal force as well. So let's see another example of finding the normal force, but this is a harder situation. Namely, let's look at an inclined plane situation. So this boy is sliding on a sled on ice through an incline, and there's no friction. We're given that there is no friction. If we draw the force diagram of the boy, I'll show the forces acting on them. So we'd have the downward weight and the normal force, which is perpendicular to the surface. So be careful how you draw the normal force. In this case, because we have an inclined plane, I'll draw the normal perpendicular to the incline, so it will be a bit tilted. It's not perfectly vertical. I have redrawn the force diagram here, representing the boy as a point. Remember, we talked about this before. When you draw the force diagram, it's nice to show the object as a single point, and thus the forces we'll have will look like this. This is the normal force. I have drawn it here, and this is the weight force. Now, once you draw the force diagram, it's very convenient to show the y and x axes so that you can find the x and y components of your forces. Namely, let's look at our figure. What is w? Let's look at n first. N is easier. What is nx? Nx is 0 because n, look at it, it's along the y-axis. It has no x component. What is ny? It's equal to plus n because the normal is in the positive part of the y-axis. If you look at wx, this is going to be w times cosine theta, where theta is the angle that w makes here. So we're given the angle w makes with the y-axis. I'll have to fix my angle. It would be 90 minus theta. This is 90 minus theta because this is theta. Now, W is in the positive x-axis here if you project, and if you project over here, W is going to be in the negative y-axis along the y direction. So I'll put minus W sine of 90 minus theta again. Now, cosine 90 minus theta is also written as sine theta from math. You don't have to do this, but I'm just showing it to you because theta is unknown. But in problem solving, theta is given to you and you don't have to change from cosine to sine. Found the x and y components of the forces. Now I can use Newton's first and second law to find the acceleration of this boy as he slides down the incline. So, as usual, I apply Newton's law along the x and y directions. Along the x direction, you can see it's written for us here. F net y is going to be equal to the x components of the forces, which are 0 plus w sine theta, which is w sine theta only, and this is equal to max. Along the y direction, I have plus n minus w cosine theta. So I'll put plus n minus w cosine theta. This is equal to may. I will deduce here the acceleration of this object. So from here, I can deduce ax is equal to g sine theta. What about ay? Okay, let's look at our figure wisely. The boy is sliding down the incline, so they are sliding along the x-axis. So ax is a itself, and ay should be 0, because the boy is not moving along the y-axis, right? The y-axis is this direction, and the boy only slides in this direction along the incline. So ay is 0. I'm going to set this to be equal to 0. Then what can we deduce? I can deduce n to be equal to mg cosine theta. I was able to find the normal force from studying the y direction. And notice how the normal force does not equal the weight only. So in fact, any question you're asked about forces, you can solve by going through 3 steps. So let's say here the boy on the sled, the question was to find the normal force exerted on the sled. I'll start by drawing a force diagram, which is where I represent the boy as a point and I draw the forces acting on this boy. And I will draw the x and y axes. Usually we draw the x and y axis to be horizontal and vertical, right? But in this particular case, it's easier to draw the x and y axes like this. Totally fine. This is the usual approach, but here I use approach. Why? I want you to see how the forces will look like if I take the x-axis to look like this. I'll have the weight force here and the normal here, and the acceleration of the boy to be in this direction because the boy is accelerating down the incline. This is a very annoying choice because you'll have x and y components for your acceleration. But if you choose the x-axis to be along the surface, which makes sense because that's the direction of motion, then you will get the acceleration to be along the x-axis. The normal will also look nice. It's along the y-axis. Only the weight force will have both x and y components. This is convenient. This is nicer because when I want to find x and y components, only the weight force will have both x and y components, which brings us to step 2. So step 2 is to find x and y components. Step 3 will be to use Newton's laws to find whatever we want to find. Here we want to find the normal force. Which of Newton's laws do I use in this problem? The sled is moving, it is accelerating down the incline, so I'll use Newton's second law, F equals ma. Now I will never use this equation as it is, I'll have to split it. along the x direction, and along the y direction. Let's get back to step 2 because we really didn't find the x and y components. Once we finish it, we can plug it in Newton's equations here and try to find the normal force, which is what the question is. So to find the x and y components of the forces, I'll look at my force diagram. This is my force diagram, this one or this one. One thing I notice, the normal is along the y-axis, so nx will be 0, and ny will be the normal itself. Any vector along the y-axis has 0x component. If we look at the acceleration is along the x-axis. So I'll actually expect ax to be a itself and ay to be 0 because a is along the x-axis, so ay is 0. Now, if I look at the weight force is more sophisticated. It's neither along the x-axis nor along the y-axis. It's a regular vector, so to find its x and y components, I'll use the formula which says that the x component of a vector is w cosine the angle it makes with the x-axis. Now, in this problem, rather than being given the angle that w makes with the x-axis, I'm given this to be theta. So I'll name this to be theta prime so I don't confuse between the two. How can I find theta prime? I'll look at this triangle. This whole triangle is a right triangle. So the angles should add up to 180. And I have everything. This is theta prime, which is what I want. This is theta, which I'm given. So let's say you're given theta equals 30. Which theta? This one. This is 30. We want to find this angle. So if this is 30 and this is 90, this is what I want, and this is a triangle. The sum of angles in a triangle should add up to 180. Theta prime is what I want. Theta is given to me to be 30, and I have a right angle. So theta prime is gonna be, just take these to the other side, and you will get 60 degrees. So I will find wx. I write it as w cosine 60. And wy is gonna be w sine 60. But I want you to be careful about one more thing. Let's look at the y component of w. It will intersect the y-axis here. This is wy. This is in the negative part of the y-axis, so I'll put a negative sign for wy. I'll add it manually. I found the x and y components of everything. Now I'll try to find the normal force. Now I want you to choose wisely here. I can work on F net along the x-axis and then along y and see which one will give me the normal force. But if you look at our equations here, nx is 0 and ny is n. So to find the normal, it's more convenient to study the y direction. Because the x direction does not give me the normal force. The normal is not even along x. Look at the normal, it's along the y direction. So I'll choose this to find n, since n is along y. So choosing the y components equation is more useful. What do we have along the y direction? You have ny plus wy equals may. What is ny? It is n. What is wy? It is minus w sine 60. This is equal to may. Now I know that ay is how much? It is 0. So I got this to be equal to 0. then I can deduce N to be equal to W sine 60. If the mass is given, let's put a given for the mass. Let's say M is 2 kilograms. So I can now easily calculate 2 times 9.8 times sine 60. I'll find that. You will get 17 newtons. This is the magnitude of the normal force. So here we made a study, a full force study, to find the magnitude of a force of interest. In this case, it was the normal force. Okay, here I have a harder case. So I'm going to be solving another problem. We have a crate of mass 100 kilograms. It is pushed at constant speed up a frictionless ramp by a horizontal force F. So the crate is pushed up, but the force itself is horizontal. So be careful of that. What difference does that make? Well, the acceleration is going to be along this direction or the downward direction, I'm not sure. All right, but it's horizontal, whereas the force is it's along the incline, whereas the force is horizontal. What other forces do we have? I have the normal force, which is like this, and I have the weight force, which is like this. As you can see, I always draw the normal to be from the incline because the incline is what's exerting it. But I can make a nicer figure where I show all of the forces starting from the same point. So what is the question? Find the magnitude of F and the force on the crate from the ramp. Force on the crate from the ramp, so the force on the box exerted by the surface, this is none other but the normal force. We want to find the normal. Let's start with part A. We want to find applied force. I will always go through the steps, where step 1 is to draw the forces. I have drawn the forces here. I'm gonna also draw the X and Y axes. It's very useful to see the X and Y axis in front of you. Now, when I have an inclined plane, I like to draw the axes to be along the incline. This is step 1. Step 2 is to find the X and Y components. What do we mean by that? We want the X and Y components of each force. So I want to find an X, and Y, Wx, Wy, Fx, and Fy. Notice how here I have this applied force as well. So, okay, let's start with the easiest, which is the normal force. Why is it the easiest? Because it's already along the y-axis. Because it's along the y-axis, then nx is 0, and ny is n itself. Now, the other forces are not as easy. For the weight in particular, I want the angle it makes with the x-axis. It has both x and y directions. So I'll write it as w cosine theta and w sine theta. So what remains is to find the x and y components of the applied force. Notice the applied force is over here. The angle it makes is this one. What am I given? I'm given this angle to be 30. I'll name this angle. Let's look at this angle. It's also 30 because these are alternate interior angles. So fx, f cosine 30. Fy will be f sine 30. Notice how Fy is in the negative side of the y-axis, so I'll plug a negative sign. Let's look at Wx and Wy. W is here. It makes this angle with the x-axis. If this is 30, then this angle is 60. So I'll just put W cosine 60. One thing I notice is that Wx is negative. It's in the negative part of the x-axis, so I'll plug a minus sign. And Wy is also negative. It's over here in the negative part of the y-axis, so I'll also put a minus sign. I found the x and y components of all of the forces. I'll proceed to use Newton's laws. Again, we want to find the magnitude of capital F. Now, one thing I see is I have drawn an acceleration vector, but if you look again at the given, we're given that the crate is pushed at constant speed. Since it is at a constant speed, then the acceleration is 0. So I'll just remove the acceleration vector from all of my study, and this makes things way easier because in Newton's laws, I'll use the first law and I'll set F net to be equal to 0. So this brings us to step 3, Newton's first law. I'll apply Newton's first law in order to find the applied force, that's the question, and then part B, I want to find the normal. Newton's first law tells me that F net is equal to 0, so F net x is 0 and F net y is 0. F net x is 0. This means that mx plus wx plus fx equals 0. And I'll just plug whatever I got along the x direction. This is what I got. I'll substitute this. I have 0 minus w cosine 60 and plus f cosine 60. Let me fix that. Yeah. So fx is f cosine 60. Cosine 30 actually, and this is equal to 0. You can see how I can work with the x equation to find f. Namely, the x equation tells me that minus w cosine 60 equals minus f cosine 30. So f is actually w cosine 60 over cosine 30. I can calculate this. The mass is 100 kilograms. So I'll get 566 newtons. I just solved part A. In part B, we want the normal force. I'll study F net y. This will be equal to 0, and this gives me, I'll just add up all of the y components over here. I'll get n minus w sine 60 plus f, actually minus f, sine 30 equals 0. Now I'll rearrange for n. N will be w sine 60 plus f sine 30. This is 100 times 9.8 times sine 60 plus, I found F, it was 566 times sine 30. I'll calculate this. I'll get 1,131 newtons. This is the magnitude of the normal force.